Good morning. We start today with David Goluskin from the University of Victoria, and long-term participant here, and he will talk about heat transport in asymptotic limits of Rayleigh-and convection. Thank you, David.
Yeah, okay, thank you. So I thought I would try to give just sort of an overview of what is known about asymptotic parameter limits, because I think sometimes when physicists discuss various scalings, it gets sort of muddied that, some of the things they're arguing about are not things that could even be made mathematically precise in the first place. So only certain of these statements are really even falsifiable. But among them, well, there's really not that much that we know. So I'm going to sort of give an overview of what we know, some ideas for open questions, and I'll show a little bit of recent work. Okay, so I know that most people are familiar with the Rayleigh-and model. I thought that I would show the equations first in dimensional form, right? So the idea is that you have a layer of fluid, the bottom is fixed to a hot temperature, the top is fixed to a cold temperature. The tildes mean dimensional for the moment. So notice in particular that, as usual, nu is the viscosity and kappa is the thermal diffusion coefficient. So it may actually be helpful to think in terms of these instead of the usual dimensionless numbers. And so you have the Navier-Stokes equations, and there is a vertical, z is the vertical direction, vertical forcing term proportional to the temperature, right? And then you have an advection diffusion equation. So this is how temperature and velocity are coupled in the Boussinesq equations. The temperature scale to non-dimensionalize is, in this case, you can just take the temperature difference between the boundaries, delta T. The height of the layer is h. G alpha is acceleration of gravity times the thermal expansion coefficient. So if you non-dimensionalize using, say, the thermal diffusion time, right, then the dimension, what happened? Okay, the usual dimensionless numbers that people use, you can only boil it down to two, are the Prandtl number and the Rayleigh number. So Prandtl is a ratio of viscosity to thermal diffusivity, often thought of as being constant in a particular fluid. Not really true, but to first approximation. And often the Rayleigh number is thought of as, say, fix everything else, but it's proportional to the dimensional temperature difference between the boundaries. So if you have a laboratory experiment, you can just turn up that temperature difference. But as I've learned from talking to a lot of analysts here, maybe you'd prefer to think in terms of kappa and nu. Right, so notice that the Prandtl number is a ratio of these diffusivities, and the Rayleigh number is inversely proportional to both of them. So if you non-dimensionalize with the thermal diffusion time scale, right, you see the Rayleigh number just appears proportional to the thermal forcing term. Everything on the right side of Navier-Stokes is now multiplied by a Prandtl number. Okay, and for the purpose of this talk, let's assume that I'm always talking about no-slip boundaries. I could be talking about 2D, 3D, horizontally, we could be periodic, we could be in an enclosed cylinder, right? But let's say that we're no slip and we're fixed temperature unless we say otherwise. And what does that look like? Well, as you raise the Rayleigh number, right, there is a finite value of the Rayleigh number independent of Prandtl at which motion sets in supercritically. Right, this is what was figured out by Rayleigh, that is the dimensionless combination that controls the linear stability problem. And if you keep turning the Rayleigh number up to, say, 10 to the 8, you get this, the physics is not rotating, just the movie is rotating. You get something that looks like this, hot fluid coming up, cold fluid coming down. So it sounds like 10 to the 8 is a big number, but the Reynolds numbers in the system are more like the square root of that. So this is, you maybe won't be surprised to learn, perhaps not an extreme enough parameter regime to give you asymptotic scaling of mean quantities that you might be interested in. Okay, and so what sort of parameter range do we have data? So in, let's say, a cylinder with its height equal to its diameter, which is a geometry in which a lot of experiments and DNS have been done. Ignore all these complicated annotations of different regimes that people are claiming. Hopefully I'll have time to talk about that later. But let's just say that all these colored dots are, notice it's Prandtl on the vertical axis, Rayleigh on the horizontal. All these colored dots are where there is some data. from experiments or simulations. And see, the Prandtl number range goes from about 10 to the -2, so that would be liquid metals, up to 10 to the 3, so that would be like a thick oil, maybe. And the Rayleigh number is going out to about 10 to the 15. Is this sort of a wide enough range to tell us about applications or to give us indications of asymptotic scaling? Well, so the Earth's outer core, I couldn't even really draw these to scale because they would be off the screen. But the convection of liquid metal in the Earth's outer core is, depending on how you estimate it, somewhere out here at a much larger Rayleigh number than 10 to the 18. Astrophysical plasmas are also way out there, and if you could have a well-defined Prandtl number, it would be like 10 to the -6, 10 to the -8. The Earth's mantle, the Rayleigh number is not that large, but the Prandtl number is effectively infinity. Right? So there's a lot of reasons that we would actually like to extrapolate to more extreme parameters. But in fact, all this existing data seem to be non-asymptotic, or at least if they are asymptotic, it's not clear enough that they're asymptotic. So you could ask about taking Rayleigh number towards infinity. You could also ask about distinguished limits where you're taking Prandtl large or small at the same time. And from these current data alone, it's not clear how you should extrapolate. Okay, that doesn't mean that these data are not valuable, right? This is a very large parameter range in which you want to know physically the answer, but it does mean that, you know, what scaling that you see in the range of this existing data doesn't necessarily lead to a mathematical statement that you could say is true or false. It just is observed, and people suggest various explanations for what they observe based on dominant balances, boundary layer arguments, but there's no limit you can take where you expect those scalings to be more and more true necessarily. Idris.
Ignorant person like me, tell me what you mean by scaling. What you're trying to show? What do you mean scaling?
Okay, so pick some quantity of interest in the turbulence, like say the mean heat transport. Take some asymptotic limit, like Rayleigh to infinity, and people generally expect that they will see a power law, like heat transport goes like Rayleigh to the maybe 1/2.
That's like heat transport versus Rayleigh.
Yeah, the power law relationships between emergent quantities and the control parameters. Thank you. Okay, so I have time to talk about only one mean quantity, so let's talk about the Nusselt number. So the Nusselt number, let us define it as this dimensionless ratio. The total vertical heat transport averaged over volume and infinite time, and you can take limb soups if you like and make everything well defined, divided by the mean transport from conduction alone. So the total is convective plus conductive, and then you're dividing by conductive. In the dimensionless, non-dimensional variables that I wrote down on the screen earlier, this is just 1 plus vertical velocity W times temperature, average over space and time. In Rayleigh-Nard specifically, I don't have time to talk about other convective systems. It's easy to show from the PDEs that this mean is related a priori to the mean thermal dissipation, the mean viscous dissipation. This is not the case in, say, internally heated convection, which Giovanni will talk about tomorrow, which creates other difficulties. But in the present case, it's true. So supposing that I fix the geometry, I fix the boundary conditions, well, now it's reasonable to say that the Nusselt number, this time average Nusselt number, is uniquely determined if you know your parameter values and you know the initial conditions, right? You know which trajectory of the system you're talking about. So to be not as careful as the analysts, but a little more careful than the physicists usually are, I think it's important to clarify what initial conditions are we asking about, right? People will just say Nusselt number, how does it scale, right? Well, there are different trajectories in the flow, different stability properties. So, okay, now you might reasonably say, well, never mind about different trajectories, I'm talking about the turbulence, right? But something to be aware of is that you don't know that there's a unique global attractor, right? And well, often in many systems, you can't prove that, but you think it's true. But in convection, especially two-dimensional convection, it is very likely not true that there's a unique global attractor. For example, in the simulations of two-dimensional convection, Prandtl number 10, Rayleigh number 10 to the 10. You can start with these are snapshots from two different states that you get just from starting with different initial conditions. One initial condition is chosen to sort of nudge the flow towards developing 6 pairs of convection rolls. This is the temperature field that's being visualized. And this one nudges the flow into 4 pairs of convection rolls. You run a long simulation, and as far as we can tell, they lock into those states. Now in 3D, it's less obvious that the states lock into different local attractors. There are experiments where people identify what look like different flow patterns. We don't know whether they're just metastable and there will be transitions between these patterns after a very long time. Sometimes yes, sometimes we don't know. But yes?
I'm going to interrupt because it's very interesting to me. Are you basically trying to assert that the dynamics in 2D is not ergodic? Because that's basically what it says. You have 2 invariant attractors. Maybe you can just repeat the question.
The question is, Idris, can you repeat the question?
I'll repeat it. So the question is the dynamics ergodic?
Based on that, not ergodic actually, not because it says that you have 2 components of the attractor, which is invariant, therefore.
Yeah, the evidence is that at least the evidence is stronger in 2D is that there are multiple local attractors and that you will really stay on one of them forever. It's not just metastable. In 3D, it's unclear whether that's true. Now, this is really an aside because I now have to jump to stress-free boundaries, but I can't resist telling you that if you have 2D domain horizontally periodic with stress-free, you can get even more different states. The only difference between these two simulations is the initial condition. And actually, there are interesting questions about whether the state on the bottom is really an attractor or just a very, very long-lived transient. But that's ongoing work I don't have time to talk about. Okay, so at the very least, even if we only care at the level of physics, if you say what's the Nusselt number, we do have to be a bit careful to say what solutions of the PDE we're talking about, because this bottom state will have very different scaling with Rayleigh number relative to the top state. Okay, but well, the simplest thing to say is that let's just say we're interested in the maximum Nusselt number among all the local attractors or the minimum such Nusselt number. Right, so the minimum Nusselt over attractors, the maximum Nusselt. But these are difficult quantities to analyze mathematically because it's very hard to, if you're proving, say, bounds, to say these apply only to steady states, attracting states. So the first thing you would do is say, well, let me relax to just talking about all PDE solutions, including the unstable fixed points, the unstable periodic orbits. Right? So of course, the minimum and maximum over all PDE solutions gives you a wider range of possible Nusselt numbers. This is all a fixed Prandtl, fixed Rayleigh. Okay, well, there's one of these quantities that we can deal with. That one's 1, because that's just the conductive state. Right? Nusselt 1 means no amplification of heat transport relative to the conductive state. The other ones, well, we really don't know how these quantities scale as you take asymptotic limits of Rayleigh and/or Prandtl, except in some cases, which I will mention. So let me just say I want to restrict attention to these 2 quantities, and I'd be happiest to know how the max over attractor scales. That's too hard. So I would settle for even knowing how the max over all PDE solution scales. That's too hard. Well, maybe not, but not solved. So let me take a bit of a side door and say, well, let me make up a related question, which is, I'm going to restrict myself to thinking about a certain subset of all PDE solutions, not the attractors, but maybe just the 2D ones, maybe just the steady states, which is, of course, a lower bound on the max over everything. And maybe I can make some progress in understanding how something scales. Okay. So I said, I want to talk about Nusselt number in asymptotic parameter limits. So the limit that people have spent by far the most time arguing about so far is where you fix the Prandtl number and take the Rayleigh number to infinity. As I said, physicists usually think of this as, oh, let's just increase the imposed temperature gradient, but maybe you'd like to think about kappa and nu, right, the thermal diffusivity and the viscosity. This limit means they're both going to 0 at the same rate. Okay, this is a singular limit in both diffusions. And well, this is in fact not a mathematical statement as far as I know, but I don't think you will find anyone on Earth who will disagree that the maximum Nusselt number among all whatever class of solution you're interested in, aside from the conductive state, is going to go to infinity, as Rayleigh goes to infinity. So all the argument is simply about how fast is this going to happen. Okay, so I'll just mention the two main predictions about what might happen in this asymptotic limit. The first one is that Nusselt will go like Rayleigh to the 1/3. This proposed independently by slightly different physical arguments by Priestley and Malkus in the 50s. Basically, what these arguments boil down to is if you assume that the presence of the thermal boundary layers are going to have a limiting effect on heat transport through the layer, you are led to conclude that the scaling should have a 1/3 exponent. Right? Basically, what happens is it can't go faster than that because the thermal boundary layer would have to get steeper, and it doesn't want to be that steep, so it has to get less steep. This leads you to a 1/3. This scaling is frequently seen in experiments and simulations. Typically at smaller Rayleigh numbers, 10 to the 5, 6, 7, you might start with a local scaling exponent that you measure that's more like 0.28, and then as you get up to Rayleigh 10 to the 12, 13, 14, you get something closer to 1/3. Okay. The other prediction, first suggested by Spiegel, although first published by Correctness, is that Nusselt goes like Rayleigh to the 1/2. Essentially, this is what you get if you assume that the boundary layers are not throttling heat transport. If you just say the turbulent bulk, you know, if you have a heavy parcel of fluid, how quickly would it sink, right? You are led to predict heat transport going like Rayleigh to the 1/2. So really, it's just talking about whether or not the boundary layers are throttling your heat transport. We know this is happening in every experiment we've seen of the standard Rayleigh-Bénard system. The question is whether it's happening asymptotically. Rayleigh number 10 to the 50, say. Okay? This 1/2 exponent has never been seen in the ordinary setup, nothing close to it, in fact. But, well, people have seen exponents slightly bigger than 1/3. You get to the very edge of your experiment range, the strongest turbulence, and maybe your exponent goes from 0.33 to 0.34 to 0.35. And there are other diagnostic quantities you can look at besides just the heat transport. And this has led people to say, oh, okay, we're seeing the beginning of a transition. There's not much data on this, but there is some suggestion in the data. Okay, I should say that this 1/2 scaling is seen if the boundary layers are somehow bypassed. So lately, people have been trying lots of modifications of the standard Rayleigh-Bénard model. You can roughen the boundaries, you can make the boundaries permeable, you can heat over a distributed region instead of just at the boundary. All of these things will allow you to achieve a 1/2 scaling. So perhaps the Rayleigh-Bénard model was not actually the best model for understanding a lot of physical systems. But if we restrict ourselves to the Rayleigh-Bénard model, nothing close to 1/2 has been observed. I should mention, certain people have asked me, well, really, who cares about this? I mean, 1/3, 1/2, what's the difference? Fair enough. But to try to get you to be a little bit interested, I would say, you know, you may have heard people mention various exponents, 3/7, 5/12. I would say the most basic question is simply, are the boundary layers asymptotically limiting? Is the asymptotic answer 1/2 or something smaller than 1/2? And you can connect this to other things people potentially care about. 1/2 will occur in this limit if and only if there are dissipation anomalies in both the thermal dissipation and the viscous dissipation. People have connected this to statements about mixing times of Lagrangian tracers. This is work by Greg Eyink and Theo Drivas. Other things. So let me show you the data. Okay, this is the data for all experiments and simulations where the Prandtl number is close to 1 or estimated to be close to 1, in experiments it's not obvious always because you're using helium close to the critical point and you're just doing your best to estimate material properties. So, well, you can see on this plot that the growth rate is typically a little slower than Rayleigh to the 1/3, but that maybe there's something happening at the upper end. In order to look at this, I really should be plotting compensated Nusselt number. So let me take Nusselt minus 1 so that it starts at 0 and goes up, and I'm going to divide it by Rayleigh to the 1/3. Okay, in this case, Rayleigh to the 1/3 scaling will be a horizontal line. Okay, here's what 2D DNS does. Initially, it's growing slower than Rayleigh to the 1/3, and then it is actually going close to Rayleigh to the 1/3. There's one data set in this regime, a recent one. Here's what three-dimensional DNS does. This is from Jorg and his collaborators, Janet Schiel, others. This also okay, so first there's, before it's kind of turbulent, and then it's growing slower than Rayleigh to the 3rd, and then it's leveling off very closely to Rayleigh to the 1/3. But I should mention that those simulations are done in a very narrow, tall domain because the simulations are extremely expensive. Okay, and then we have experiments done in low temperature helium or sulfur hexafluoride. There are 3 data sets. One of them seems to be doing something dramatically different, but this has not turned out to be reproducible. And I suspect that there are some non-Boussinesq effects or issues with estimating the material properties because this is low temperature helium and it's very hard to map the experiments onto the Boussinesq equations reliably. In fact, you might be surprised to hear that the experiment that people sometimes think is the strongest evidence for a transition to a larger than 1/3 exponent is this purple one. You can see that the quality of the data is very good. There's very little spread. And if you look at the very end, there is an uptick. So I don't want to get into it. People analyze this very closely, look at all different data, but let's just say I think it's totally unclear as Rayleigh goes to infinity whether you will continue to see 1/3 or not.
The fact that you see a different multiplier is because they're all different geometries or something else?
Yes. So unfortunately, some of these are horizontally periodic. Some of them are in cylinders. So this is why you have a different prefactor in different experiments. Okay. So what has been said mathematically? Well, people can try to put an upper bound on this maximum over PDE solutions. That's too difficult to do directly, so you want to somehow relax the maximization. And what people have done is you drop the Navier-Stokes equations, except you retain this one integral balance from it, which says that the vertical convective heat transport is related after time and space average to the viscous dissipation. Right? And if you then consider just the advection diffusion equation subject to a certain budget of viscous dissipation, well, you could actually relax the maximization a bit further and get a tractable upper bound that scales like Rayleigh to the 1/2. So, well, in terms of scaling, this really hasn't told us anything because I don't think any physicist would have thought any larger exponent is conceivable. But, there's no basic back of the envelope argument that gives you this prefactor. So I think having this prefactor, this one particular smallest prefactor comes from Plastine and Kurzweil, is of value. And also notice that it's uniform in Prandtl. Right? The fact that it's uniform in Prandtl tells you, well, it will tell you, for instance, that you can't have heat transport going like Prandtl to the 1/2, Rayleigh to the 1/2 if Rayleigh and Prandtl are both increasing, for instance. Okay, and you might say, well, this is actually an upper bound on this right-hand maximization problem, so maybe we can work harder to analyze this right-hand maximization and get a smaller exponent, but it turns out that this is not true. There are, constructions of these complicated branching velocity fields by Tabasco and Doring, which show that up to logarithms, if you're not actually using the Navier-Stokes dynamics, this maximum can't be smaller than Rayleigh to the 1/2. Okay, so now what? Our data says that the maximum of Nusselt over attractors is growing at least as quickly as Rayleigh to the 1/3. There's no mathematical theorem to that effect. We can't seem to get the upper bound with a smaller exponent in general. We can do things if it's 2D stress-free, if the Prandtl number is getting large, but in general, we can't do that. Well, as I said, I'm gonna now show you some results on this easier problem, which may or may not have relevance to the main question, because here we can make some progress. In particular, I am going to consider only the simplest solutions in this problem, aside from the conductive state. I'm just going to consider this is a bifurcation diagram, Nusselt versus Rayleigh. The simplest steady solutions, which are these pairs of convection rolls that bifurcate in the instability first identified by Rayleigh in 1916. And let me fix my domain in this picture, although I could allow it to be infinite. So the first one that bifurcates might just be a pair of convection rolls like this, and then you could get another bifurcation of steady rolls where you're fitting 4 of them in your domain, or a 2x2 grid of them. And if you look at these steady states, if you go along a steady state, this is not obvious, but if you compute them out far enough, you will find Rayleigh going, or Nusselt going like Rayleigh to the 1/4. On the other hand, you could look at the envelope over all of these branches, and I'm going to try to convince you that this will make it look like Rayleigh, Nusselt going like Rayleigh to the 1/3. So if the class of solutions I'm considering is just these simplest roll states, then I'm claiming that the maximum Nusselt over these states goes like Rayleigh to the 1/3. So the computation of these was initiated by Leslie Smith and Fabian Willef and their postdocs in these 2 papers in 2015. And all the results that I'm about to show are essentially suggested by their results, but their computations are just not quite in the asymptotic regime. So Rayleigh took these 5 or 6 decades farther in the Rayleigh number in order to figure out what the asymptotic scalings really look like. That's the one thing I'm showing you that's from a recent paper. So here's the paper. And so what we're doing then is computing the Nusselt number for steady rolls with all different horizontal periods for a pair of rolls. So gamma is the horizontal period of a pair of rolls. So I'm plotting versus wave number, so the inverse here. So the widest rolls I'm computing are the ones on the far left. These have aspect ratio 2. And the narrowest rolls are the ones on the far right. And this is a Prandtl number 1, Rayleigh number 10 to the 9. So first of all, there's some interesting behavior here. This was originally found in this paper by Sondak, Smith, and Willef, which is that you in fact have multiple local maxima of the heat transport as you vary the width of these steady states. But I'm just going to focus on the global maximum here. And I'm going to call the horizontal period of those rolls gamma star. And if you want to keep increasing the Rayleigh number and keep making the heat transport as large as you can, it turns out that you want gamma star to be slowly decreasing like Rayleigh to the -1/5. Okay? If you don't do that, if you just fix the aspect ratio of your roll branch and go up to Rayleigh 10 to the 10, you can see that this is a compensated plot of the Nusselt number. So you can see that the Nusselt number is growing slower than Rayleigh to the 3rd. But if you do make the rolls more and more narrow as you increase the Rayleigh number, you'll find that the Nusselt number is asymptotically, I would claim, approaching Rayleigh to the 1/3 scaling. And to see this more closely, let me just plot the local scaling exponents. So for these fixed aspect ratio states, after some abrupt transition that's actually kind of hard to explain, the scaling exponent is going very close to 1/4. And for the optimized ones, it's going very smoothly, I would say, to 1/3. I mean, the measured exponent for these last few points is already larger than 0.33. How does this compare to DNS data? These are those compensated data that I showed you already. Let me add the Nusselt numbers for steady states with a fixed aspect ratio. You can see the trend here is that these will eventually lie below all the turbulent data. But if I plot the ones with the optimized aspect ratio, it lies above all the turbulent data, except for this one data point that I don't really believe. So this was already observed by Smith and Waleff that the scaling of these optimized rolls is comparable to turbulence. And we are further observing that it is, in fact, larger in all the experiments that are sort of similar enough to make a direct comparison. So I don't know whether this maximum Nusselt over steady rolls has anything to do with the question that we really care about, which is the turbulent scaling. But I hope, given you strong computational evidence that this scaling is Rayleigh to the 1/3, and there is a possibility that it might be that these are actually the maximizers of Nusselt number among all PDE solutions. So this is something that Idris asked Sergey about the other day. This is this statement. I don't know if that's true or not, but if it is true, it gives you sort of a side door to trying to prove something about the max over all solutions that's smaller than this upper bound that we have. You could try to prove that the steady states are the maximizers, and then you could try to prove something about steady states, for example. Okay, so that's the state of what's known about the Rayleigh to infinity asymptotic limit. I mean, there's tons known about convection in very important pre-asymptotic regimes, but not much is really known about what happens asymptotically. What about some other limits? What else should we think about? Well, suppose only kappa is going to 0. Let's not send the viscosity to 0. If you fix the viscosity and send kappa to 0, that's actually sending Prandtl to Rayleigh at the same, Prandtl and Rayleigh to infinity at the same rate. If you want to send Prandtl to infinity with fixed Rayleigh, you actually have to send viscosity to infinity like the inverse of kappa. So you could take any sort of distinguished limit in this quarter of the parameter plane. I should say, first of all, that any limit where Rayleigh is getting smaller is not interesting because convection will cease to occur and you'll just have no heat transport. So there's sort of two quarters that are interesting, the upper right quarter and the lower right quarter. So you could try to take different distinguished limits in here. If you simply take the Prandtl number to infinity with fixed Rayleigh, this is the one of these limits that's not too hard to understand. In this case, we know that the maximum Nusselt number is going to approach a finite constant. Because in this case, you have such a thing as the infinite Prandtl number equations. If you look at the way that I non-dimensionalize the Boussinesq equations, you'll see as Prandtl number is becoming larger, you could think that these three terms on the right-hand side are going to balance each other, and the left-hand terms will become irrelevant, right? And that is what happens. So you have like a Stokes flow, except that the Stokes equation here just gives you velocity in terms of temperature. So this is still a nonlinear dynamics because then this term in the advection diffusion equation is basically quadratic, non-local in temperature. But there's rigorous theory by Wang in 2004 that says solutions to the full Boussinesq equations, Cauchy problem, will approach solutions to the infinite Prandtl equations as you take the Prandtl number to infinity. So we have some understanding of this limit, but this is sort of asking about taking Prandtl to infinity using the infinite Prandtl equations and then taking Rayleigh to infinity is one way to do it, but you could also ask about taking Prandtl and Rayleigh to infinity at the same time. So here I'm talking about distinguished limits where Prandtl and Rayleigh are both going to infinity. Okay, so if you take the infinite Prandtl equations, Constantine and Dorian prove that the Nusselt there is bounded by Rayleigh to the 1/3, and this is very, very likely to be sharp. There are logarithms, so let's not discuss logarithms. This is very likely to be sharp. If you do simulations, you I think can see something very close to 1/3 in the infinite Prandtl equations. But you could also ask about other distinguished limits. And I think this is a very interesting result by Camilla, who's here, and her two co-authors, which says that in order to get an upper bound with an exponent of 1/3, you don't need Prandtl going to infinity faster than Rayleigh even. You only need Prandtl to go to infinity at least as quickly as Rayleigh to the 1/3. So this is a limit in which viscosity is not even going to infinity. It's just going to 0 slower than kappa. And if you are in this other wedge where Prandtl is going to infinity but not as quickly as Rayleigh to the 1/3, they also produce an upper bound that is asymptotically smaller than Rayleigh to the 1/2. Right? So sometimes when people propose things about scaling theories non-rigorously, they say things that are provably false. Right? You cannot have Nusselt going like Rayleigh to the 1/2 with a uniform prefactor in any region of parameter space that allows you to take Prandtl to infinity at the same time, no matter how slowly. And so I think people should be more aware of this. Okay. I think that's all I have to say about the upper right corner of distinguished limits. What about the lower right corner? Right, well, okay, let's fix kappa and send nu to 0. So if all that's vanishing is the viscosity, that's like sending Prandtl to 0 inversely to the Rayleigh number. On the other hand, if you want to send Prandtl to 0 at fixed Rayleigh number, then you need kappa to go to infinity at the same time that the viscosity is vanishing. As far as I know, there is basically nothing known analytically about this bottom right quadrant of limits other than the upper bounds that are uniform in the Prandtl number. Right, so, okay, Anna convinced me the other day that sending nu to 0 is a very difficult limit, but perhaps the fact that you get to send kappa to infinity at the same time might make something easier to do analytically. And in particular, let me just show you some computational evidence. I think that the maximum Nusselt number decreases towards 1 as Prandtl goes to 0. As far as I know, that's a simple statement. That just says heat transport goes back to the conductive state. This is seen very robustly in any simulation that tries to take the Prandtl number smaller. But as far as I know, there's nothing rigorous analytical said about this. Here's some data. This is at a small Rayleigh number because that's all I had on hand. These simulations are by Hannah Swan and Sasha Lenin, two undergraduates working with me, and some steady rolls are computed by Bao Wen. So the bottom data points are what you get in three-dimensional simulations. So here I'm starting on the right at a Prandtl number of 1. To the right of this, the Nusselt number tends to be pretty flat with the Prandtl number, and indeed it has to be flat as Prandtl goes to infinity. So I'm just looking below Prandtl equals 1. Right? And we can do these 3D simulations, and you can see that the Prandtl number is increasing relatively quickly. But look at how small the Nusselt numbers are. Nusselt minus 1 here is less than 1/2. Right? So this is like a very conductive fluid. So when the fluid wasn't moving, it was already conducting heat well. So it's difficult for convection to improve on the conductive state, is one way to see that. Something that occurs at small Prandtl that doesn't really occur at large Prandtl is 2D and 3D become very different. Notice that there seems to be a different rate at which Nusselt is dropping off for the 2D data. And this is, I think, very interesting. The steady rolls at a fixed aspect ratio, as Prandtl is going to 0, the Nusselt number is dropping off incredibly slowly. This is something like Nusselt is going like Prandtl to the 1/40. Okay, so if you look closely at it, it does not seem to be flattening out. But this is why I think it would be of interest to try to prove that the maximum Nusselt over all PDE solutions, regardless of stability, really does decrease back towards 1 in this limit, because you will never see it in computations because of how slowly it occurs. Okay. Let me show you some two-dimensional simulation data, just because the 3D data wasn't quite ready, at different Rayleigh numbers. These are Rayleigh numbers of 10 to the 5, 6, 7. There are Nusselt versus Prandtl scalings here. You can kind of see in the middle data series. reasonable power law looking thing on this log-log plot. We would like to say something about this scaling. Physically, of course, you can just do the simulations. You can measure a power law. You would then like to make a mathematically precise statement, such as I take Prandtl to 0, such and such is the scaling I expect to see. But I think that's actually not the right thing to do. Because I think when you go way, way, way to ridiculously tiny Prandtl numbers that you'll never find, even in a star, I think that this scaling will change. So asking for some sort of mathematical statement about this power law, you do not want to fix Rayleigh and send Prandtl to 0. I think what you need to do is you need to take a sweep where you're making Prandtl smaller and you're making Rayleigh larger so that you stay in this regime. And then you could make some kind of claim about the asymptotic Prandtl dependence in this regime. There's various limits you can take, but there's a few reasons that I think what you actually want to do is take the distinguished limit where Prandtl is inverse to Rayleigh. This is not something people have really looked at, partly because both of those limits make simulations more expensive. And in experiments, well, you can't really freely tune your Prandtl number. Your fluid kind of is what it is. But to some extent, the simulations are doable, and I have students working on this. So I think you particularly want to look at the limit where the viscosity is vanishing, but the thermal diffusivity is fixed. Right? This is Prandtl inverse to Rayleigh. And if you look at different scaling predictions that have been made in the literature, they essentially are consistent with saying that this will also be a limit in which the Nusselt number is asymptoting to a constant, as in the infinite Prandtl number limit. But I know of, I mean, it's a well-posed mathematical statement, or it could be made one, but as I know of no way that this is close to being provable. I think I have a little time, right? 5 minutes or something. Okay, I figure since people have mentioned these Grossman-Losa scaling predictions once or twice, I could comment on whether these have relevance to the questions that I'm talking about. Okay, so what did Grossman and Losa try to do? Really, the key ideas are all in the original 2000 paper, even though there are various follow-ups that make things more complicated. The idea is existing scaling theories basically are thinking about fixing Prandtl and making the Rayleigh number large. They have no hope of coming to terms with the fact that different experiments in different regimes observe different local scaling laws. So what the original paper in 2000 tried to do was systematically make different predictions for different scaling regimes. And it's all boundary layer arguments and dominant balance arguments. But it's done in a systematic way where you say, you know, in this regime, the thermal boundary layer will be thicker than the viscous boundary layer, or vice versa. In this regime, this dissipation will be dominated in the bulk versus the boundary layers. And you wind up with a bunch, and then, right, assuming you've built in the correct asymptotic scalings in different directions, you arbitrarily patch these different scalings together with some sort of arbitrary functional form that's like a crossover function. And then you fit to data. So there are, I don't know if you can see them, 4 red squares on this picture. Those are 4 different, so they have 4 fitting parameters. It's kind of a lot, but they are predicting certain scalings and certain limits. So you're kind of baking in certain information. Okay, but, I would say in terms of non-asymptotic scaling, this is accomplishing something, right? Because you want to, you want to do a fit to data in a way that is somewhat informed by physics. On the other hand, what do their predictions say about asymptotic scaling? Not that much, really, because in many of these regimes that they draw, there is no asymptotic limit that you can take to get a falsifiable statement. Right? So regime 1, 2U, 2L, there's no limit you can take here that's asymptotic. Regime 1 infinity, well, you can take Prandtl to infinity, but we already know how that scales. Regime 3U, if you take the limit that keeps you in that regime, it just collapses to be the same as the other regimes. So if we're only interested in asymptotic predictions, many of these regimes are no longer relevant. These two regimes, their predictions say Rayleigh to the 1/3, just like the old Spiegel and Malkus predictions. And I would say that that is very likely true. That's what happens if you take Prandtl number to Rayleigh number at least this quickly, which is at least as quickly as Rayleigh to the 2/3. And that's, Camilla's result says that you can't go faster than that, and data says that you probably do achieve that scaling. Okay, so the real difficult question is what happens over here if you take Rayleigh to infinity, either with Prandtl fixed or Prandtl going to 0. It's actually very hard to pin down what the prediction about this regime is from the Grossman-Losa theory. In this little boxed region, which is not an asymptotic regime, they predict Rayleigh to the 1/2, Prandtl to the 1/2. The difficulty is that there are no further predictions in their original systematic series of arguments. This dash dotted line here is sort of tacked on afterward to say this is where we estimate the Reynolds number to be such that boundary layers become turbulent. But there's nothing in the original predictions that say exactly how that should affect the Rayleigh-Prandtl scaling. And if you read different papers, they predict different things. I think the first paper says that this Rayleigh to the 1/2, Prandtl to the 1/2 scaling should occur in all three of these regions. Well, that is provably impossible, right? Because in region 4L prime, that would allow you to take Rayleigh and Prandtl to infinity, and you would have Nusselt going faster than the upper bounds. Even taking Rayleigh to the 1/2 uniform in Prandtlism is not possible in region 4L prime, because Camilla's result says if Prandtl is going to infinity with Rayleigh, you have to be asymptotically smaller than Rayleigh to the 1/2. If you read somewhere else, maybe the claim is that this region is Rayleigh to the 1/2, Prandtl to the negative 1/2. That's not contradicted mathematically. But I think a useful first step would be to clarify what exactly is the prediction and is it consistent with the known mathematical results. Certainly there is some regime, probably down here, where I think people would predict Rayleigh to the 1/2, Prandtl to the negative 1/2. And that's consistent with this speculation I made that taking Prandtl inverse to Rayleigh should make Nusselt go to a constant. Okay, so I think these are, if you're interested in asymptotic behavior and precise statements, these are the various limits and how they relate to this scaling theory. So some questions, particularly for mathematical analysis and computation. Right, the first one is it really true that steady states maximize the Nusselt number among all solutions? If not, well, find a periodic orbit that transports more heat. If so, I think it's conceivably provable, but very difficult. Is it true that if you fix Rayleigh and send Prandtl to 0, that the Nusselt number goes down to 1 for all states? This seems difficult to prove. It relies certainly on the velocity boundary conditions. It is false for stress-free boundaries. And I showed you that for no slip boundaries, if you're looking at unstable steady states, it can be very, very slow trend. And then I'm also thinking that people hopefully should think more about scalings in data or bounds that could possibly be proven for heat transport in this distinguished limit where you're sending Prandtl to 0 as Rayleigh goes to infinity, perhaps at an inverse rate, which would be exactly fixing kappa and sending the viscosity to 0. Okay, thanks.
Chat. Rich, can you just one second? Reach us to Rich. You can unmute yourself and ask your question, please.
Yeah, hi. Thanks, David, for that talk. I guess you can see me. I don't know if I can see myself actually, but anyway.
I see you.
Could you go back to your nice 2D parameter space of Prandtl versus Rayleigh, where you had all those arrows? That's it.
Yeah, hold on. I see. Yeah.
So I'm not used to thinking about the one going sort of diagonally upwards through the top right corner. I'm sort of more used to thinking of the one going straight up. So you take Prandtl number going to infinity first, and then Rayleigh to infinity.
Yeah.
Do you get the? So my question is, do you get the same if you do Prandtl to infinity and then Rayleigh number to infinity, as taking them both to infinity, where they're related by a constant ratio?
Yeah. So the result by Camilla and her co-authors is that if you send Prandtl to infinity at least as quickly as Rayleigh to the 1/3, you get the same 1/3 scaling upper bound as if you sent Prandtl to infinity first and then used the infinite Prandtl number equations.
Great. Okay, so that constant that you've got at the top of your diagram is basically an increasing function which goes off as Rayleigh to the 3rd.
It does not go faster than Rayleigh to the 3rd, and it probably goes exactly like Rayleigh to the 3rd, possibly up to logarithms.
Great. Thank you very much.
Mm-hmm.
So let's go to the famous Losa-Grossman diagram. Okay, so this was presented to the world at a Santa Barbara, we now call it Kavli Institute, turbulence meeting in the year 2000. At that point in my life, I was between jobs. And the last thing I could do was to get up in public and explain to the world why there was more than one problem with that diagram, because I was actively doing many Prandtl number simulations at the highest range of Rayleigh numbers that anyone could do in the year 2000. So from a historical perspective of where Grossman and Losa thought they could create this diagram, those of us who are old enough know about the Ortsager-Haupt renormalization group solution for turbulence, which Greg Eying did an incredible service to the community and deconstructed that entire edifice. On that basis, every single one of those regimes has its own little assumption. How can I say that? There's a regime somewhere in there which was the regime of the experiments that Gunter Allers was actively doing at Santa Barbara, and it did not fit into their diagram before that. I should also point out that I couldn't say anything, but Losa was getting up and basically overpowering with his voice everyone who tried to object to his great theory. So Gunter got up and said, hey, I have these experiments. They don't fit into your diagram. What happened? Well, the next day, they came back and, oh, yes, I have this new little thing I can do, a little fill in that gap. So I could say more.
What's the question?
I'm making a point. I couldn't make this point in the year 2000, okay? As I pointed out after Jorg's talk, there is a group in Munster who have redone many of these simulations and basically said what I tried to get published, but Losa suppressed in the year 2001. My last thing was something in PRL, and then I had to change my life completely. So make note of that. There's no point in us trying to even think about this diagram.
Well, I don't think what I have said is an advertisement for this diagram. What I'm saying is that if you want to produce statements that are falsifiable, most of the diagram is not relevant. Maybe it's useful for fitting, maybe it isn't. Right? The only question you can ask is whether in 1, 2, 3 regimes of this diagram, whether that's the correct scaling when you take a distinguished limit.
Yeah, thanks, David, for very nice talk and exposition. there's sometimes because we are a diverse community, there is some kind of like communications issue about concepts. So you talk about solutions of the differential equations, yet you have to take long time average, which is basically you are near sort of attractor. So it's not just solutions, because you have to look for long time behavior, which is you are near kind of attractor. The other thing is when you talk about attractors, I mean, there are many concepts of what you call attractors. So it was not clear to me. There is concept which we call global attractor, which is include all the steady states, all the time periodic solutions, all their unstable manifolds. That's where basically turbulence is occurring in that sense. And so that's why I wanted to check with you. I mean, you talk attractors versus solutions. Can you be more specific about these issues? I mean, maybe we can talk later. I mean, if you don't have the time, but I wanted to basically clarify there is the issues of definitions of what's called, and it varies from one community to other.
Yeah. So, well, I mean, as you know, in 3D, these things are not even proved to exist. Right? These locally attracting states. I'm not talking about global attractors. When I said attractor in this talk, I'm talking about what a physicist would call the observed turbulent state. What you're talking about the Lorentz attractor, right? That has some measure that you can define on it. What is that not the answer?
Okay, Camila was first.
I'm a bit embarrassed to use the microphone, but anyhow, so sorry. Hi. So I mean, mathematically, going to Prandtl, going to zero, so let Prandtl go to zero is very challenging. Okay, for many reasons, boundaries and so on, dimensionality. So, but you seems to have a precise picture in mind on what should happen in the limit Prandtl goes to zero. So I wanted to ask you. So where does this intuition come from? Because I think you have really a picture, and if there are also numerical simulation somehow.
Well, maybe you're overestimating my intuition. It comes from this, right? If you look at the data and take Prandtl smaller, Nusselt is getting smaller. And if you poke around and look at, even some unsteady rolls, it's still the case. Physically, it's because the temperature profile is going back toward linear. If you fix Rayleigh number and take Prandtl to zero, right, you'll see that the temperature profile is returning to linear because the fluid conducts heat so well that even though the Reynolds number is not getting small, right, it's just sort of the heat will just return close to its conductive equilibrium, even though it's being stirred by a larger Reynolds number. So maybe it's very hard to prove something with no assumptions about that limit, but as we discussed the other day, if you're willing to put some assumptions on the magnitude of the velocity field, you can perhaps make use of a statement saying that the temperature distribution remains close to linear.
I think you showed another picture, so another plot, and so I was wondering about the dimensions. So here you say 2 and 3D.
Yeah, those are numerical integration. And
in like the classical configuration of periodic sidewalls and
these are horizontally periodic. Yeah.
Okay, thanks.
Oh, I have a very short question. You showed the non-uniqueness of states at high Rayleigh number. You showed with different pairs of rolls, but at one point you mentioned, so I was surprised to hear that survived up there, but at one point you mentioned a classical configuration of 1-to-1.
Yeah.
Is there non-unique? I mean, those were all pairs of rolls. Is there non-uniqueness also in a 1-to-1?
In a 3D cylinder, you mean?
3D or 2D or whatever you want. Does it require a larger aspect ratio?
No, in 2D you could probably get it. In 3D,
you could get what?
You could probably get more than one configuration to remain locally stable.
Even if the aspect ratio was 1.
I don't know about 1, 2, yes. I mean, there's a limit. If you make it narrow enough, you can't get rolls side by side, but you can get them to stack vertically. I would say in 2D, usually it's possible. In 3D, it's not clear ever if it's really possible, or if maybe you're just looking at metastable states that are just different wings of the same attractor.
Nice talk. It's just along the lines what Edris said, but different, also terminological issue. You are talking about distinguished limits, not mentioning intermediate limits. And for people working in asymptotics, that makes it kind of incomplete and unclear, but it is much better to discuss the soft line. I'm just saying, like, well, we need to sort this out, but that's terminology, nothing.
Okay.
Question for, is there a question in the chat? No? Okay, so let's thank David for the talk.